So now we have our environment set up for Game Boy game development, it's time to jump into how the Game Boy displays graphics. The Game Boy has 3 layers where we can display graphics. We've got the background layer, which is a scrollable tile of background elements. We have the sprite layer, which typically has the character that can be moved around and other enemies in games. And then we have what's called the window, which is normally for the heads-up display, displaying some coins or some overhead stats, or whatever you might want in the game that sits on top of all the other windows, or whatever information you typically want displayed permanently throughout most of the game. We're going to start by exploring this first layer, the background sprites, as well as how the Game Boy handles tiles and sprites and grids, and understand exactly how we can create tiles and sprites manually, as well as using some tool-assisted design. And let's get some tiles up on the background layer. So let's just jump in and see how we display tiles in the Game Boy, and then we'll fully dig into the exact binary representation so we understand exactly what we're doing. Okay, so let's just start with some information about the Game Boy for those that don't know. This is a good little site with a little bit of information. So this will be available on our RetroSix.wiki page, which will contain all links as we go through this development process, so that we can keep one place for all the links. You can obviously see the link here as well if you want to type it in. But let's just scroll down and take a look. So obviously this is the Game Boy for those that don't know, the Game Boy DMG as it's called. This is the original Game Boy. And the main thing we're interested in when doing the game development is the actual screen at the moment. So we can see here the screen is 160 pixels across by 144 down. So this little monochrome display, it's 160 pixels going left to right and 144 pixels down, so slightly off square. You can see it has 4 shades of grey, so effectively it has 4 colours. One is effectively transparent where nothing's on, one's light grey, one's dark grey, and one's solid black. The overall video memory is only 8 kilobytes total, so that limits us to how much we can store and display. But this is the key information here we want to focus on. So as I mentioned, there are 3 layers to the Game Boy. We have the background, the windows, and the sprites. All of those use tiles because the Game Boy is a tile-based graphic system. So it mentions here the tiles are 8 by 8 pixels in essence, 8 by 8 bitmaps. And they are typically referred to as a tile set or a tile pattern table. So here is a pattern table where every 8 by 8 bits here, for example, the 0 is one tile, then number 1 is another tile, 2 is another tile, and you can kind of easily distinguish that they are split into 8 by 8 pixels. We're going to make one of these tile sets ourselves and then display them. And you can see if we put the grid on, you can see where it divides the tiles. So everywhere in between that grid is a tile. And then a single one is like this. It's just made up of 8 pixels across, 8 pixels down, and it can either be white, black, dark grey, or light grey. So it's quite an easy graphic system to work with. We have the background. So as we can see here, the background is made up of 256 by 256 pixels. So the screen's only 160 by 144, which means your background is typically in memory larger than the screen. That's what allows for easily scrolling the background and loading in the background as an infinite scroll as it moves across the screen. You can see here's the visual representation. If this was a 256 by 256 pixel background, this is showing here where the Game Boy physical window might be displayed, showing this amount of graphics at one time. And then as you scroll up or down, this window would move around and that's what you see. But behind the backgrounds, there is a 256 by 256 background we can make use of. The window sits above everything else, and you typically have the window displayed something like this, and then in code, scroll the window all the way to the bottom so that it doesn't hide everything that's behind it. We'll come to the window in another lesson. And the same with sprites. Sprites are typically individual tiles or multiple tiles, usually called meta tiles, made up of several tiles that sit in the middle, so on top of the background and behind the window. The overall result then in a game would look like this. We have the background, as you can see. We have the 2 sprites here that can move independent of the position on the screen. And we have the window here, which has been scrolled to the bottom to form a kind of heads-up display. So what we want to focus on first, considering the Game Boy as a tile-based system, is how do we make these tiles? What does it represent in code, and how does that code map back to an 8x8 pixel grid? After that, we will display them in a background, in windows, and in sprites, all the same. So for now, let's focus on tiles and how they're designed. At the moment, I don't think there's a very good cross-platform tile designer that works on Mac, Linux, and Windows, so that might be something we design in future. But for now, the most common one is this Game Boy Tile Designer. You can download it for Windows, or if you're on Mac, you can run Parallels, which allows you to run Windows applications. So we're going to use this to design some tiles, but we're then going to look at how that maps to actual bytes in memory and what those bytes mean, so that you could design tiles without any tools if you liked, but it also helps you to understand what's going on instead of just relying on the tools. So when things go wrong, you actually have an understanding of how tiles are formed. As well as the tile designer, you might want to get the map builder, which we'll come to after, in order to make background maps. So on the background layer, it's simply made up of tiles at set locations that then form maps. For now, we'll do the map manually once we understand how the actual tiles are designed. So that's all the tools we really need. If we just crack open Visual Studio Code, all I've done here is copy and pasted our read buttons folder, pasted it into background tiles, and deleted everything so we just have a main. If we press F5, this should build. Open up the emulator, and you can see here I have open from the Tools menu the Tile Map Viewer, and you can also open the Tile Viewer to see individual tiles like this. So you can see by default, without doing anything, when the BIOS loads that opens this emulator, the tiles here are already set to display the Nintendo logo. And as I hover over with a mouse, you can see it kind of indicate and show each tile, which is an 8x8 tile. So what we want to do is create our own tiles. So for that, we open the Game Boy Tile Designer, and you can see here we have 8 pixels by 8 pixels. We have over here the tile map, so this is the tile pattern where you have lots of tiles. We try not to call it a tile map because when we make maps which use tiles, it can get a bit confusing. So we'll try and refer to this as the tile set or the tile pattern. But the tile set seems to be what makes more sense. It's a set of tiles. And as you can see here, this is the 0th tile, this is the first tile, the second tile, and you can go as many as you like, so long as they fit into memory. So in this tool, we'll click the 0th tile, so effectively the first tile, but 0 index. You can see down the bottom here, we have the 4 colors. So we have the white, the light gray, dark gray, and black. So if we select black and click, we can draw some shapes here. This is the single tile, and this is the tile for when you want to make a kind of repeating tile. If I right click as well on here, you can select the right click color, and then you can see here left and right indicating the left mouse button is currently black, the right is 0. So you just left and right click here to set the right colors for your mouse clicks. So if you leave the right click as 0, it's kind of like an eraser, and the left click is the color you want to use. So without being too concerned about drawing anything specific in here at the minute, we want to understand how the bits inside of here map to data inside of the game. So for that, let's just draw, say, a few dots in specific locations and maybe a few different colors, just so we can try and get a grasp of how the code that's output by this tool relates to the pixels on screen. So here's just a random thing I've drawn. If we then go File, Export to, we want to change this to GBDK as a C file. We will browse to our folder, and we'll call this our tile set. So we'll call this number tiles because we will eventually make this into some numbers. We'll match the label name, so number tiles, and this is just the name it will give it in the code file. We'll make sure the format is selected to Game Boy 4 color. In advanced, we leave everything unchecked, and we just simply click OK. This will generate the number tiles C file, which we can now see here. And we can see in this file there's some information telling us that it's an 8x8 tile. It's tile 0 to 0 because in the tool, when we did export to, we selected the range from 0 to 0. So we're only exporting one tile at the moment. And then you can see here's the tile. Now, just so we can display this on screen and get something working so you can visibly see that tile, we'll just come into main, and what we first have to do is fill this tile set into the Game Boy's memory. So for that, we do set underscore background underscore data, and this is loading the tile set into memory. So the index of the first tile to write, we want to be 0, the first tile, and then the number of tiles to write. Well, there's only one tile in this tile set, and now it's asking for a pointer to array of those tiles. So if we jump up here and do include, and then we do number tiles to include this file here, and you'll notice when it's local, we use the quotes instead of the angle brackets, and the quotes mean to look in the relative path. So in this case, we want to look in this folder. Now we've imported this file, we can refer to it as number tiles. So we go into here then and just type number tiles. This will load tile set into Game Boy memory. Once the tile set's there, we need to now show those tiles somewhere. So you can use a background map, which we haven't created yet, but we can also just do init background and basically fill the entire screen with a certain tile from the tile set that's been loaded. So in this case, if we pass in 0, that's all we need to do, it will use the 0th tile from this numbers tiles. So we only have one in there anyway, so it's going to load the first tile and fill all the background with that tile. So fill entire screen with first tile. Now the only thing left to do is to actually show that background, because in the Game Boy you can turn the background on and off, which is good for some visual effects, or whenever you want to do something or reload the background and you want to hide it while you're doing it. There's reasons you want to show and hide it. So we call this macro show background. That will now force the background to actually show on the Game Boy. And then we turn the display on. So that's the minimum amount of code we need. And what we should now see is something similar to this here. We should see this tile repeating over and over. So just press F5. And there we go. The Game Boy screen is now full of this single tile. We can see on the tile viewer over here, if you look closely down the bottom, you can see this must be the background tile set because we've loaded the tiles into the background and it's showing here as the first tile in the memory. There's obviously clearly tiles here, which we'll come to after, and there's clearly a third set of tiles here. But what we're interested in right now is our tile set has been loaded there as number 1. Here's the background we were on about. This is the 32 by 32 tile background, which is 256 by 256 pixels. And this black border here is the actual Game Boy display window, which is this big window here. So just to visualize what's happening here, that the background has been entirely filled with our tile that's larger than the display window, let's just chuck in a simple scroll. So infinitely, we can just do scroll background, and then the number of pixels we want to move in the X, the number of pixels we want to move in the Y. We can then do a slight delay so that it doesn't move too quick. Press F5, and now you can see our background appears to be scrolling. You can see here, this is actually the display window here, this square here, and that's just a representation of this larger window. So you can see what happens in memory when we scroll the background. We're actually just moving our viewport. When it gets to the end of the screen here, you can see it loops back to the start of the background. So this is what we're looking at here. This is currently the right side of the screen, and this is the left, and it's overlapped. So hopefully that gives you a visual idea of, here is your tile set where you can load all of your tiles into memory. This is the background that is 32 by 32 of those tiles large that we can fill with any combination of our tile set data, and that gets displayed on the screen, which currently we're simply displaying all over the screen. So now let's focus on these generated bits of information and how they map to what's displayed here. So the best way to do this is to open up the Windows calculator, go to programmer mode from the left menu, and then we can click hex here. And if we just move this down here, so if we click hex here and type 88, you can see the binary here says 1000 1000. Now if we look at this, it's fairly obvious to see we have 1 as in a dark colour, 000, 1, 000. So we can see it kind of maps to what we're seeing in the screen. However, there are 4 possible colour options, so that means every single pixel on the screen can be either 0, 1, 2 or 3, hence the numbers here. So we can't possibly represent it with a single bit. However, there's a clear indication that this layout matches this first row. You can see the next byte is 88 again, so that means we have 2 sets of this exact same binary information. So let's move on to the next byte here. The next byte is all zeros, so that would be just a bunch of zeros, and the next one is 88 again. So we have 1000, 1000. So if we just try and visualize, the first 2 bytes here in binary are 1000, 1000, and the same again like this. This is the equivalent of the 8888. The next set is all zeros and then 8888. So there's another one that is represented like this. So if we take a look, it doesn't take much work to figure out what's the difference between the first row of 8 pixels and the second row of 8 pixels, represented by this is the first row, this is the second row. Well, clearly the first row is solid black and should be the number 3. And the second row is the number 2, the dark grey, and that would be represented by the number 2. You can also see, based on the pattern of where the bits are, that it looks like the bits are literally a representation from left to right of where the colour is. If we take a look in the calculator and go to binary and clear this off, if we put 0 in binary, it would represent the number 0. If we put 1 in binary, a single bit, it would represent the number 1. If we put 0, 1 in binary, it represents the number 2. And if we put 1, 1 in binary, it represents the number 3. So what we're looking for, to represent white, it would be 0, 0. To represent light grey, it would be 0, 1. To represent dark grey, it would be 1, 0. And to represent black, it would be 1, 1. So if we take a look at this data here and we presume that the first byte and the second byte go in order like this, so the first pixel is made up of this bit and this bit, we would get 1, 1, which would be black. You can see here it is black. The next 3 would be all zeros, which they are, 0, 0, 0, and then black, 0, 0, 0. Moving on to the next row, with it being dark grey, we should have the number 2, 0, 0, 0, 2, 0, 0, 0. So if we look at this row now, you can see if we took this bit and this bit, we would have 0, 1, which would give us light grey. We want 1, 0, so what it must mean is the first byte is what's called the least significant bit, so the bit that would be placed furthest to the right if you're writing out a binary number. And the second byte is the most significant bit. So if we wanted to represent 1, 0, and the left side is the most significant bit, then we would take this number first, the most significant bit, and then this number. So it would be 1, 0, which is dark grey. We'd then get 0, 0, 0, 0, 0, 0, which is what we want. Then 1, 0 again, repeating the pattern, and we get the equivalent of what we see on screen. So what should we expect to see for the third row of pixels? Well, we have light grey, so we'd expect to see 1, 0, 0, 0, 1, 0, 0, 0. So we want to see zeros on the most significant bit, and we'd expect to see 1 on the least significant bit just in the first 2 spots. So we'd expect to see this. So if that's what we're expecting to see on the third row, you can see clearly these 2 bytes make up the first row. So it's 2 bytes per row. These make up the second row, the third row, the fourth row, the 5th, the 6th, the 7th, and the 8th. So altogether, 16 bytes will represent an 8x8 tile. So we've worked out before converting the hexadecimal to binary that the third row, so row 1, row 2, row 3 here, should be 10001000 for the first byte, which is this 88. So if we go to hexadecimal and type 88, you can see we correctly get 10001000. The next is 0, which is all zeros. So we've figured out how the formatting works for writing bytes and it then representing some colours on screen. So if we were to just erase this and click File, Export, you'll see that this file should instantly update. We'll have to close it down and not save because we've been typing into the file. But if we go back into the file, you can see that it updates. So if we wanted to play around and see changes, if we were trying to understand this format, we could click, say, the light grey and put it in the first patch and do File, Export, and you can see this instantly update to 80. You could put that in the calculator and type 80 in hex and see that the first least significant byte is now 1 and then all zeros. So you can see there's kind of an indication that this is where the colour lies. You could go all the way along the row and do export, and you can see now the first byte turns into FF, which if we put in hexadecimal is all ones. We could remove, say, the middle two and export, and we get EF. We type that in, and you can see clearly the change in colour represented in the binary format. So we're quite comfortable now that that is the format of these bytes understood. That means if we wanted a tile, we simply have to create 16 bytes. If we want more than one tile, let's say we have multiple tiles, and we do another one here, full of info, we just have to do export to, and change this range from 0 to 1. And now you can see it's added the second tile. So all this is a bunch of 16 bytes multiplied by however many tiles we create. And every 2 bytes represents one full row of 8 bits in a tile. We have all of the least significant bits of the 8 pixels in the first row, and then all of the most significant bits of the 8 pixels in the first row. And then it repeats for the second row, the third row, and so on. So with that now, we want to make a bunch of numbers. I've already gone ahead and created that file. There's plenty of free pixel art and kind of number graphics online that you can grab, or you can just literally draw numbers if you're used to drawing them. You can draw letters the same way, you could add shading. So it's really up to you. We could say grab the lighter color here and do a kind of shadow of the number and make a sort of Mario style shaded number, or we could just stick to flat as is. So I'll just stick to the flat numbers, and the reason I've done this at the minute is so when we come to make a tile map that basically picks certain tiles based on this index number here to display on the screen, if we pick tile 0, it will display a number 0. If we pick tile 1, it displays a number 1. Pick tile 2, it displays a number 2, for example. So I've done this for a reason. So let's now just export this. So export to, and we want tile 0 to 9. So if we do 0 to 9, we can see now we have the number tiles here. If we now change our number tiles in here to reference that we have 10 tiles because there's 0 to 9, which is 10 tiles, press F5 to run the code again. And we can see in our tile grid down here, you can see all the tiles loaded to memory. If we were to now change this number, say for example, initialize the background with tile number 5 or index 5, which is the 6th item in the list, it will display the actual number 5 now. So you can see why I've kind of done that to purposely allow us to easily start creating tile maps and understand how these tiles that get loaded into the background end up getting mapped to a tile map. Now, just out of curiosity, if you comment out initialize the background, and you comment the scroll background so nothing moves, look what happens when you now load the default screen with nothing initialized. You can see here what would be the Nintendo logo. Whenever you turn a Game Boy on, you will typically see the Nintendo logo scroll down and stop around here. And this little hole here looks like it's clearly going to be the registered trademark symbol, which you can see in the tile map here. So what it looks like is the tile map has already been set to display tiles number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, probably 13, and going along like this. And if you go to the tile map viewer over here, and in fact you can even hover over and see that this is what is actually happening. It's selecting and showing you over on this side here what tiles are mapping to those positions. Now if you look at the tile set here above, you can clearly see if where we saw a 0, we went to this tile map. Where we saw a 1, you went to this tile map. You can see the start of the N. You can see that this would have been Nintendo loaded into memory. So what you're seeing here is actually where Nintendo was loaded in to the virtual memory, to the VRAM, and we've simply now updated the tile set from the Nintendo tile set to our tile set. It also shows that by default the background gets filled with random information. So what we would normally do is initialize the background with a blank tile, and what we would also normally do in our tile set, we would normally keep the 0 tile as a complete blank tile, so that we could just initialize with 0. Because we want to understand how the tile map works first, I wanted these numbers to actually be written in the index they're in. For now, we could change this to initialize the background to tile number 10, which is something we don't actually have. We only imported 0 to 9. But we can see by default, it's currently a blank tile. Our tile sets are blank by default. If we wanted to be sure, we would either update this and export to the 10th tile, or because we understand already how this works, we can just add 16 bytes of 0 here. So if we just do 1, 2, 3, 4, 5, 6, 7, 8, copy again, there is our now 10th tile of all blanks, which will give us a true blank tile. And we can tell this that we're actually loading 11 tiles in now. And then that prevents this from possibly loading any random jargon that might be in RAM. And we're guaranteed that we should load an empty background. So let's just set this to now be a random number like 6 and scroll the background. Just so any of you playing around with this get to actually visually see something. Next up, we want to actually make potentially a background map of what could be a game and understand how tile maps work. So I hope this has helped you understand how the Game Boy is displaying on screen, how the tile sets are created, and how the binary data represents those 4 colours of information. So next up, we'll take a look at tile maps. But that's it for this one. I hope you learned something and enjoyed this. Any feedback or suggestions, feel free to leave them in the comments, and I get back to as many as I can.